Okay, so our device was the Dexcom G6 integrated glucose meter. So some of the stuff we're going to cover is the introduction. We're going to go through some of the methods we used to gather our data on how this device works. And then we're going to go through some of the results of these methods and have a little bit of discussion about them. The picture on the screen kind of shows what the device is and what some of the different classes of these type of devices. There's just a regular blood glucose meter, which is used for reading glucose levels in diabetic people. Then there's that's the first one is just a general class 1 device, and then it goes up to a class 3 device for the intermittent and real time. And then the integrated one, which is the one that we're actually covering, is only a class 2 device, which I'll talk about that a little bit more on the next slide. So a brief overview of the product. It has the particular one that we're using has 3 different parts. It has an auto applicator, a sensor and transmitter, and then the actual display device. The auto applicator is used to insert the sensor under the skin, and then the sensor actually measures the glucose levels and sends them to the display device, which is a touchscreen receiver that shows the levels in real time. This is one of the first FDA-approved continuous glucose monitoring devices that is able to integrate with other devices. Most of the other ones are standalones. They don't actually integrate with iPhones or anything else. This one's classified as a type 2 medical device, so it's a moderate risk class instead of being a class 3 like other ones that I talked about on the past slide. So this one's also approved for use with both type 1 and type 2 diabetes. So here's a brief video of how the device works.
It starts with a tiny sensor. You wear it right here for up to 10 days. You forget you have it on. You can shower with it, work out, whatever. The sensor measures your glucose levels just underneath the skin. And a transmitter is fastened on top of the sensor and sends data wirelessly to a receiver or compatible smart device. Now here's where it gets interesting. Each of these dots is a glucose reading, taken 5 minutes apart, so you can see how your glucose levels are trending over time. But the app also has arrows that show the speed and direction your glucose is heading. 2 arrows down mean you're dropping fast. 1 arrow down means you're dropping more slowly. Red means you're below your set target range. Yellow means you're above your set target range. Gray means you're within your target range. Steady, boring, wonderful, in range. So much information just by glancing at your smartphone or receiver. With the Dexcom G6, you can manage your diabetes with 0 finger sticks. Yeah.
Moving on to the methods of human analysis, I'm Luke, and we're going to look at the light, vibration, and noise used by this device. So the display device utilizes all 3 as part of both normal operations and alerts. The auto applicator, sensor, and transmitter all do not have indicators of any kind, so it's only the display device that we're going to be looking at. And the display device's screen turns on and lights up whenever the main button is pressed and during alerts. And these alerts are displayed on screen and are signaled by multiple short vibrations, followed by 2 loud beeps. Looking specifically at the alerts, one of the issues our experienced user reported was alarm fatigue. On average, it took the experienced user 6 to 7 alarm cycles to address the receiver's alerts. And an issue that was identified was that the receiver emitted a similar alarm for an important glucose warning, say too high or too low, as it did for a simple loss of signal, which is usually unimportant according to the user. And the user reported loss of signal alerts happening from just sitting too far forward relative to the position of the receiver, or having their computer sitting too close to the sensor. And these issues usually remedy themselves momentarily and pose no harm to the user. But on average, this loss of signal alarm goes off for the user once every 2 to 3 hours. And looking at this, it's easy to see how that would get very tiring very quickly and might cause the user to miss very important alerts.
I'm Steven, and the next kind of method we used to kind of gain understanding of the product and the process was hierarchical task analysis, obtained through video analyses, just kind of looking at some experienced users as well as some videos that are already online, tutorials and stuff, and kind of using all these videos to gain an understanding of the total process. And by doing this, we're kind of able to define the most critical elements of the process and how to carry out tasks that are involved with this device. Ultimately, this allows us to kind of break each element into sequential steps and descriptions and allows us to gain a crucial insight into kind of the manual and intellectual activities of the device itself, as well as any personnel who are operating, maintaining, or controlling the system. So ultimately, through all the analyses we have, we kind of are able to break the process down into one major objective, which is obviously to monitor glucose, as the device is literally made for. But from there, you kind of break the process into two major halves, one being physically applying the sensor and transmitter, while the other is kind of the setting and using the receiver and getting data from that. Kind of delving into the physical application part, you start with prepping the location, usually just rubbing isopropyl alcohol and an adhesive patch. Next step is kind of to engage the applicator. That little handle looking thing with the orange button on it in the top left corner is the applicator. So you stick that to the adhesive and insert the needle or tube, which actually physically puts the sensor into the interstitial fluid inside your body and kind of allows it to get those readings. Once you remove the applicator, that sensor gets left behind on your skin. And then you click the transmitter, which is that little black piece under the handle, into the sensor. And that's obviously what transmits the information to the receiver. So on the receiver side, setting up the receiver, you just connect the receiver to the sensor by adding serial information and pairing with Bluetooth. Once that's connected, you kind of just calibrate by doing manual blood drawing, by finger pricking, or however, to make sure that the readings are consistent and are correct. And then the last part is kind of just to set your limits, as every single person is different. Some people's high or low levels of glucose might be different for some other people. So the last part is kind of just set your limits where you can kind of manage your alerts and personalize and show your trends and graphs and stuff like that. So after kind of gaining more of an understanding of the process through that hierarchical task analysis, we kind of move forward with summative or validation usability testing. Ultimately, we kind of did this to see if the graphical user interface of the device could potentially cause manual errors or any deviations. So we conducted a quick validation testing on samples of random Clemson students, and we had 15 random participants per group and two distinct groups, which we kind of divided as experienced users and inexperienced users. We essentially presented them with the user interface and asked them to navigate the interface without any aid. As the FDA suggests, you want about at least a 90% objective of success, which we kind of defined as success as being able to navigate the user interface and interpret important results, visuals, and graphs in a timely manner. And then afterwards, we conducted a short post survey where we basically just gather information like if they had any previous experience, if they could easily navigate the user interface, and just an open-ended side where they could kind of talk about any complaints, complications, or just areas of improvement that anyone saw in the device. And ultimately, with this little table that we have on the right, you can kind of see what you need in order to achieve that 90% objective of success, where we tested about 30 people in two groups of 15. And ultimately, it went really well, and we only had about one failure per group, which falls into that upper confidence level that we really want.
I'm Brandon, and moving on to the results. When looking at the usability test, we found that 28 out of 30 participants successfully completed each task that was assigned in under 10 seconds. 14 out of 15 inexperienced users were successful, and 14 out of 15 experienced users were successful. The times to navigate the user interface were relatively similar from an experienced user to a participant with very little to no experience using the interface. The post-survey results indicated that 28 of 30 users felt as though they were able to navigate the interface efficiently and effectively. Here's an example of a sample usability test that we did. It was for the simple task of opening the screen and getting to the main page of the device. We had a pass-fail limit of 10 seconds that was used throughout. You can see from the results that experienced user 4 failed at the time of 13.8 seconds, and inexperienced user 6 failed at the time of 11.9 seconds. You can see that the average of the times for the experienced users was around 4.64 seconds, and the average time for the inexperienced user was around 5.42 seconds. So they were roughly pretty much around the same amount of time to complete each task for this sample. Moving on to our user complications. Overall, many users were satisfied with the device as a whole. However, 5 users did have some complaints or troubles with the device during the usability testing. These were sampled through our survey. We found that delays between touching the screen and getting a response from the interface were pretty substantial to some users. There was also issues with pressing some on-screen buttons due to their size, which led to accidental closing out of important menus. And our experienced user within the group also found the following complication with the device, and this was alert fatigue that we mentioned earlier, caused from multiple unimportant alarms that have similar sounds to various important ones within the device.
I'm Sydney, and I'll be going over our discussion/takeaways. Based on the results, the overall interface of the Dexcom G6 device is simple and easy to navigate for both experienced users and inexperienced users, considering both types of users were able to complete the usability testing with the same pass-fail rate. The results also indicated the device is relatively easy to navigate for both types of users, as the times to complete each of the assigned tasks were relatively similar from an experienced user to an inexperienced user with no outstanding differences. With regards to the few complaints received within the survey, as well as from our experienced user, the group would suggest to impose the following changes to the device. First and foremost, updating the touchscreen system/software to increase response time when various buttons are pushed. Secondmost, to increase the button sizes within the interface to reduce error in misclicking or accidental closing of the menus. And thirdly, incorporating new distinct sounding alarms to allow for easy understanding of important/unimportant alarms, or to gauge the difference between various important or unimportant alarms, as well as to increase volume and pitch, as well as to provide rapid vibration for highly important alarms, and to provide an audible alarm that says the type of alert to allow for a greater understanding.